So I compared this with e to the minus, beta h, and I said that beta is a length. Aha. Well, in relativity, lengths are as good as times, right? So that means that in terms of dimensional analysis, this quantity here, beta h, acts just like this one here. So there should be an h bar here, right? But the temperature, I said, was 1 over beta. So it's really h bar over beta. And the temperature goes to 0 as h bar goes to 0. Okay. All right. So this is good, because let's just think about thermodynamics for a moment. Suppose I have any thermodynamic object. Yes, question. Good. Let me get there. Let me say this first. I, in fact, want to talk about the second law right now. So let me first take the classical limit where there is no Hawking radiation, okay? Because there's no Hawking radiation because the temperature goes to 0. And as we all know, if I have an object at 0 temperature, it doesn't send out any radiation, right? Okay. So now, just think for a moment about any thermodynamic object which always has 0 temperature, no matter how much energy it contains, and which has infinite entropy. Okay? Well, it's always got 0 temperature. So that means that when you put it near anything else, energy flows into the 0 temperature object, right? Energy always flows from hot to cold. That's the way it works. So it absorbs all kinds of things and never sends anything back out. Sounds like a black hole, doesn't it? Indeed it does. Indeed it does. So it's very interesting that many properties of black holes in the classical limit are well reproduced just by any thermodynamic object. Okay. Also, let me do one more. Not only is S infinite, but as we said, ds was dm over t. And since t goes to 0, this also diverges. That is to say that the change in entropy between one black hole and the next larger one is also infinite. Okay? So what does that say about the second law? The second law says that entropy for the entire universe, if you like, universe, should not decrease in time. It should either get bigger or stay the same. Right? That's the second law of thermodynamics. Okay. Well, again, suppose h bar is 0, and there are black holes around. Okay? If there are black holes around, then if any black hole got smaller, or suppose there was one black hole in the universe, okay? If that black hole got smaller, its entropy would decrease by a negative infinite amount. And there's no way you could make up for that in any other process. Right? So the second law suggests that at least classically, the total surface area of all black holes put together should also be non-decreasing. It should also only get bigger as time passes. Okay? And this is a classic result in general relativity, which you can prove from the Einstein equations. It was proven by Stephen Hawking first. And so this is called the Hawking area theorem. Okay. It's true. It's just you can prove it in classical general relativity. So this is a certain bit of consistency of the whole story. I should mention, for completeness, that although this is called the Hawking area theorem, and Hawking proved the first version, it turns out the version he proved doesn't apply to the real world. Okay? It turns out the version he proved assumes too much makes stronger assumptions about the horizon than are true in real life. However, this has been recently fixed in a lovely paper by Crucial, Galloway, and a few other collaborators. So you can look these folks up. So really, we should call it the Crucial, Galloway, something else, Hawking area theorem. But so-called the Hawking area theorem. Okay. All right. So I'm just showing you that things fit together in the classical limit where h bar is 0. But what about the case, you say, where h bar is not 0? What does the second law say then? Well, when h bar is not 0, then the entropy of black holes is finite, and therefore black holes act much like any other object. The thing which is non-decreasing should be the total of the total entropy in black holes plus the total entropy in everything else, which we will call matter. Okay. So quantum mechanically, we expect that only this total needs to increase, which could happen in several ways. It could be that in some process, both these quantities increase. It could be, on the other hand, that the matter entropy shrinks and the black hole entropy grows. This is the kind of thing one is familiar with, because if, for example, we take a star and we throw it into a black hole, the star is now gone, so the matter entropy has gone down, because the star is gone, it's been eaten by the black hole. But the black hole gets bigger, and so it grows. Okay. But there's a third possibility as well, which would satisfy this. It's possible for the black hole to shrink quantum mechanically, so long as the entropy of other matter goes up by a correspondingly large amount. And that's exactly what happens in the Hawking process. In the Hawking process, negative energy comes into the black hole, so the black hole does, in fact, shrink. Okay? But as we said, the black hole throws out a large number of particles. And it throws them out as thermal radiation. And you may recall that thermal radiation has the most entropy that you can pack into a certain amount of energy. So it throws out a lot of entropy. And most importantly, it does this very slowly, so that by the time the black hole radiates much of its energy, the first bit of Hawking radiation has traveled a very long way across the universe. So it not only emits this thermal radiation, but it spreads it across an enormously large region. And as you may know, whenever you have a gas or photons or what have you, and you allow them to fill up a very large volume, that generates a lot of entropy. Right? This is the famous adiabatic expansion of gases, that this configuration, where I have gas molecules all over a box, has more entropy than this configuration where I have them packed into a quarter. Okay? So the answer to your question, therefore, is the Hawking process satisfies the second law because it takes place in a large volume of space. And it disperses the radiation across a large volume. One can consider what happens if one does what's called black holes in boxes. You try to put the black hole in a small cavity so the radiation cannot disperse. In that case, the Hawking process, it's not quite correct to say that it stops, but what it does is it fills up the cavity with thermal radiation, and then the whole thing comes into equilibrium, and the black hole doesn't decay anymore because it has then reached its state of maximum entropy. Okay. For those of you who know anything about anti-de Sitter space, or the ADS-CFT correspondence that Clifford Johnson mentioned very briefly yesterday, anti-de Sitter space acts to a certain extent like a finite box, and this is what you find in anti-de Sitter space. A black hole in anti-de Sitter space, which is sufficiently large, knows that it's in a kind of box and remains stable and does not evaporate through the Hawking process because of the second law, because it would have to reduce its entropy to do so. Okay. Right. Okay. Good. So this is interesting. But perhaps the most interesting thing about the entropy of a black hole is just the fact that when h bar is not 0, we do have a finite result. Okay? Because, after all, let's see. This is where the real mystery is, in my opinion. It's why is the entropy of a black hole finite at all? Now, normally it's not a problem. If you have a system like a box of gas, you do a calculation of the entropy, it comes out finite, right? Why is that true? It's true because you do a calculation. Let's say you use what's called the microcanonical ensemble, which means maybe you fix the total energy. So you want to count the number of states with a certain energy inside the box. Well, if I try to add more particles, the energy goes up. If I try to make the particles, if I try to take the particles' wave functions and make them too narrow, the energy goes up. That's quantum mechanics. So it's the fact that you only allow a certain amount of energy that makes the number of states inside a box finite. Now, what about the black hole case? Well, certainly, again, we want to fix the energy. We have only this much energy to work with, that times c squared. But now we have a problem, which relates to our previous discussion. Because inside the black hole, there are both, as we said, positive and negative energy states. And if there are both positive and negative energy states, then it's hard to see why we can't keep adding particles that have positive energy and simultaneously add ones that have negative energy and let them cancel out and still have mass m. So this is a deep mystery. Black holes, in some sense, appear to have a finite number of states. And as I mentioned, there are, well, the question is then, why should it be true? Or perhaps, is there some other interpretation of this entropy? Is it perhaps somehow possible that really the black hole has an infinite number of internal states, but somehow only a finite number count? That might be another logical possibility. And that's an open and sometimes hotly debated area of research. Okay. Other questions before I say a few minutes about holography? No? All right. So I was requested to say something about holography, and I will now do so, having gone through the appropriate background. So this term holography, let me just remind you where it comes from. Holography. It's related linguistically to the word hologram, which I would expect that probably you've all heard of. This is the process where you use lasers and interferometry to record a three-dimensional picture of an object on a two-dimensional piece of film. Okay. So, in fact, I probably even have one on my credit card someplace. Many people do these days. So this is a process that encodes three-dimensional information into two dimensions. And the point is that black holes remind some people of holograms. And why is that true? Well, we've been talking here about thermodynamics, right? Okay. Suppose one considers thermodynamics of an ordinary system. Thermodynamics of, let's say, of photons. Okay? Then suppose I give you a bunch of photons in a box, and I ask you, well, suppose I more properly take a box and heat it to some temperature. And I ask you, what is the entropy in this box? Then it's a standard thermodynamic calculation, I'll just write down the answer, that the entropy is roughly the temperature cubed times the volume of the box. Okay. Right. So